3 problems worked through from beginning to end. They share one decision, and you are made to take that decision 3 times, once for each of them. Here is the decision. Some expressions do not care about the names of their letters. Take x plus y times y plus z times z plus x. Swap any 2 of the 3 letters, and you get the identical expression back. Nothing moved. An object like that is called symmetric, and the first claim here is that the symmetry is not decoration. It is information. It is telling you the letters are interchangeable. So when a problem hands you something symmetric, you have a choice. Protect that symmetry and look for the object that holds it, or destroy it deliberately and grind. 3 problems. 1 decision made 3 times. And the answer is not the same all 3 times. Problem 1. 3 different numbers and 1 question about their product. 3 different numbers. They add up to 6. Multiply them in pairs x times y, y times z, z times x, add those up and you get 9. Now multiply all 3 together. How big can that product be? That is the whole problem. No calculus prerequisites, no famous theorem, nothing you have not already met. What makes it worth an evening is that there are 2 ways in, and they disagree about almost everything. One of them refuses to touch the numbers at all. The other attacks them immediately. They arrive at the same answer, and, as we will see at the end, at the very same curve, without ever knowing it. First, notice what kind of object this is. Swap any 2 of the 3 letters x for y, y for z. It does not matter, and every single condition comes back unchanged. The sum is unchanged. The sum of pairwise products is unchanged. The product is unchanged. An expression like that is called symmetric, and symmetry is not decoration here. It is information. It tells you the 3 numbers are interchangeable, that the problem cannot tell them apart, and neither should you. Which raises the question that this whole episode turns on. Should you protect that symmetry or destroy it? Take the first road, keep it. If you refuse to separate the 3 numbers, you need an object that holds all 3 at once. There is exactly one natural candidate, the polynomial that has them as its roots. Build it. A cubic whose roots are our 3 numbers has, as its coefficients, precisely the quantities we were handed, the sum of pairwise products and the product. So the equation is t cubed minus 6t squared plus 9t minus the product. Look at what just happened. The 3 unknowns are gone. They have been folded into a single curve, and the question about them has become a question about that curve. Now the question reads, for which values of the product does this cubic have 3 different real roots? And that is a picture. Draw the curve t cubed minus 6t squared plus 9t, and slide a horizontal line up and down. The roots are the crossings. 3 crossings means 3 different numbers. Measured from the derivative, the curve turns at t equals 1 and t equals 3. At 1 it reaches 4. At 3 it comes back down to 0. Above 4, the line cuts the curve once. Below 0 once. Only strictly between 0 and 4 does it cut 3 times. So the product lies strictly between 0 and 4. Done. Now the other road, and it begins by throwing away everything we just admired. Count what you have: 3 unknowns, 2 conditions. 2 conditions can pin down 2 unknowns. So the product is not really a function of 3 variables at all. It is a function of 1. That is the entire idea. No elegance, no structure, no clever object. Just pick X, let the two conditions determine Y and Z, and see what the product does. Notice the difference in posture. The first road thought carefully before moving. This one starts moving and expects to think later, if at all. So grind. From the first condition, y plus z is 6 minus x. Substitute that into the second, and the product y times z becomes x squared minus 6x plus 9. Multiply by x, and the thing we want is x cubed minus 6x squared plus 9x. But we are not finished, and this is where the brutal road charges its fee. We need y and z to actually exist, and to be real, and to be different from each other, and to be different from x. Each of those is a condition on x, and each one has to be computed. No insight will save you here. Only patience. Here is the toll computed. Y and z are the roots of a quadratic, so they are real exactly when its discriminant is not negative. That discriminant works out to minus 3x times x minus 4. Non-negative only when x sits between 0 and 4. They differ from each other exactly when that discriminant is not 0, which removes the endpoints. And x differs from both of them exactly when a second expression is non-zero. Squaring and simplifying gives 12x squared minus 48x plus 36, which vanishes at x equals 1 and x equals 3. So x roams the open interval from 0 to 4, with two punctures at 1 and 3. Those two punctures split the road into 3 pieces. From 0 to 1, from 1 to 3, from 3 to 4. Watch the product on each. On the first piece it climbs from 0 up to 4. On the second it falls from 4 back down to 0. On the third it climbs again from 0 to 4. Every piece sweeps out the same interval measured here. Each one covers 0 to 4 and nothing beyond. 3 separate journeys, one shared destination. The product lies strictly between 0 and 4. The brutal road arrives. Late and out of breath, but it arrives. Now put the two roads side by side, and look at what each one wrote down. The careful road produced t cubed minus 6t squared plus 9t, the curve whose crossings are the 3 numbers. The brutal road produced x cubed minus 6x squared plus 9x, the value of the product itself. Those are the same cubic. Not similar. Identical, and not because we tried numbers. Expand the second root and the coefficients come out 1, minus 6, 9, 0, exactly the first. It is an identity between polynomials, so it holds for every t there is. A numerical sweep agrees at the points we sampled, as it must. And yet they mean entirely different things. On one road the curve is a container holding 3 unknowns. On the other it is the answer, plotted directly. 2 people, working in opposite directions, spent the whole problem staring at the same curve, and neither of them could see the other. The argument is finished. The interval is proved, and nothing below adds to that proof. What follows is a check on our arithmetic, on the algebra we did, and the code that drew these curves. We generated 200,000 actual triples. Pick x, solve the conditions for y and z, discard the cases where they collide, and keep the ones that genuinely satisfy both conditions. Every triple was verified. The sum is 6. The pairwise products sum to 9 to within machine precision. Then we looked at the products. Smallest observed, 0.0000. Largest observed, 3.9999. Not one of the 200,000 left the interval, and both ends were approached but never touched. That is not why the statement is true. It is true because of the derivative and the three crossings. This is only evidence that we made no slip along the way. The proof set an open interval. The experiment agrees, digit for digit. Problem 2. Two numbers standing at the same height, and the point nobody asked about. Two numbers x and y. They are not equal to each other. Take the first one, cube it, then subtract 3 times its square. Do exactly the same to the second one. The two results come out the same. That is the entire condition. X cubed minus 3x squared equals y cubed minus 3y squared. Nothing else is given. No sizes, no signs, no second equation. And the question is about their sum. How large can x plus y be? How small? There is no obvious place to push. Notice that the condition is perfectly symmetric. Swap the two letters and it says exactly the same thing, while the quantity we want is symmetric too. So we will start twice from opposite ends and see which road is kinder to us. Before choosing a road, one translation. Whatever the shared value is, call it A. Then x and y are both solutions of the same equation. T cubed minus 3t squared equals A. And that has a picture. Draw the curve u equals t cubed minus 3t squared, and draw the horizontal line at height A. Saying that x and y give the same value is saying that the 2 points sit at the same height on the curve. The condition was never really about cubes at all. It was about a horizontal line and where it cuts. Once you see it that way, the whole problem becomes a question about intersections, which is the kind of question a picture can answer. Keep that image. One road will use it, and one road will refuse it. Road 1 refuses the picture entirely. It works with the letters and nothing else. Bring everything to one side. X cubed minus y cubed minus 3 times the quantity x squared minus y squared. Both of those differences share a factor. X cubed minus y cubed contains x minus y, and so does x squared minus y squared. And x minus y is definitely not 0, because we were told the numbers differ. So we are allowed to divide it out. That division is the whole decision of this road. It is legal, it is one line, and it deliberately destroys the symmetry we were handed. What remains is a single equation in 2 letters with no structure left in it, nothing elegant to hold on to, and nothing to think about either. From here it is only work. What survives the division is x squared plus xy plus y squared, minus 3 times x plus y, equals 0. Now name the thing we actually want. Let k stand for x plus y. Then y is k minus x, and we can push that substitution through. Expand xy as x times k minus x. Expand y squared as k minus x squared. The x squared terms partly cancel, the cross terms fold together, and after the dust settles the whole thing collapses to something small. X squared minus kx plus k squared minus 3k equals 0. A quadratic in x with k as a dial. Every choice of k either admits a real x or it does not, and that is now the only question left. No insight required. Just care. Now the fences go up. For x to be a real number, the discriminant cannot be negative. Compute it, k squared minus 4 times k squared minus 3k. That simplifies to minus 3k times k minus 4, an upside-down parabola through 0 and 4. It is non-negative exactly when k lies between 0 and 4, inclusive. But we are not finished, because the problem also demanded that x and y be different from each other. They coincide precisely when x equals k over 2. Substitute that back and you get 3/4 k squared minus 3k, which vanishes only at k equals 0 and k equals 4. So the two forbidden values are exactly the two endpoints we just found, strictly between 0 and 4. Road 2 keeps the picture and changes what it looks at. Fix the height up and ask for every t with t cubed minus 3t squared equal to a. Move everything to one side and it is a cubic equation. T cubed minus 3t squared minus a equals 0. A cubic has 3 roots. 2 of them are the numbers we were given, x and y, the 2 points where the horizontal line meets the curve on either side. But the line usually meets the curve a third time, and that third crossing is a number the problem never mentions. It is not x. It is not y. It has no name and no role. Most solutions discard it without a thought. Watch what happens when we refuse to. Call that third root z. Now use the one fact that ties all 3 roots together. In the cubic t cubed minus 3t squared minus a, the coefficient sitting in front of t squared is minus 3. And for any cubic, the sum of the roots is that coefficient with the sign flipped. So x plus y plus z equals 3. Always. For every height we might have chosen. Rearranged, that says the quantity we are hunting, x plus y, is simply 3 minus z. Look at what just happened. We do not need to find x. We do not need to find y. We never have to solve the cubic at all. The entire question has turned into a different one. How far can the point we discarded actually travel? So sweep the line and watch it move. First, the shape of the curve. Its derivative is 3t squared minus 6t, which is 0 at t equals 0 and t equals 2. The local maximum is 0 at t equals 0. The local minimum is minus 4 at t equals 2. Between those two heights and only between them, the horizontal line cuts 3 times. Now slide the line slowly upward from minus 4 to 0 and follow the leftover point. It starts near t equals minus 1, walks right along the curve, passes through the dip, climbs the far side, and ends up near t equals 3. It sweeps the whole stretch, continuously, missing nothing in between. That range is the answer in disguise. Except at the two ends, where we have to be careful. Push the line right up to the peak. There the 3 roots are 0, 0, and 3, a double root at the top and one far crossing. The only pair of genuinely different numbers we can pick is 0 and 3, so the leftover point is 0, not 3. The value 3 is never actually left over. Drop the line to the very bottom and the mirror image happens. The roots are minus 1, 2, and 2. The only distinct pair is minus 1 and 2, and the leftover point is 2. Minus 1 is never left over either. So both endpoints are punched out. 2 open circles, 1 at each end, and everything strictly between them is reached by something. Now put the 2 answers side by side. From the picture, the discarded point z runs strictly between minus 1 and 3. And k equals 3 minus z, which flips that interval and shifts it, giving k strictly between 0 and 4. From the algebra, the discriminant allowed the closed range 0 to 4, and then a separate check knocked out the 2 endpoints by hand. 0 to 4 open at both ends. The same interval reached twice by 2 roads that share nothing. One of them watched a point move along a curve and never wrote down a quadratic. The other wrote down the quadratic and never looked at anything. Neither one is wrong. They are simply not doing the same kind of work. The proof stands on its own, the discriminant on one road, the third root on the other. What comes next proves nothing further. It only checks that we did the algebra correctly. Here is the experiment. Sweep the height across its entire allowed range, and at each height solve the cubic numerically to full precision. Keep the roots that are genuinely real and genuinely distinct, form every valid pair, and record their sum. 600,000 pairs. For every single one, we also verify the original condition directly. That x cubed minus 3x squared really does equal y cubed minus 3y squared before the sum is counted. The smallest sum observed, 0.00000. The largest, 4.00000. Never outside the interval. Never sitting on either end. The proof said open. The measurement agrees. Problem 3. An expression that looks symmetric and is not. 3 positive numbers. Build this. X over x plus y over y plus z over z plus x. Call the whole thing A. 2 questions about it. First, show that a lies strictly between 1 and 2. Second, find exactly when A equals 3 halves. Before starting, look carefully at what kind of object A is, because this is the place where people usually hesitate. A is not symmetric. Swap x and y and the first term becomes y over y plus x, which is fine. The denominator did not change, but the second term becomes x over x plus z, and that is a different expression. The whole thing shifts. It has the appearance of symmetry without the property. And that is exactly what makes it interesting. Road 1, keeping the symmetry, meets an obstacle immediately. There is no symmetry here to keep. So it does something better. If the symmetry is missing, produce it. Write down a second expression, b, which is a with every numerator replaced by the other letter in its denominator. Y over x plus y, plus z over y plus z, plus x over z plus x. Now add a and b together, term by term. The first pair is x plus y over x plus y. The second pair is y plus z over y plus z. The third is z plus x over z plus x. Every single one collapses to 1, so the total is exactly 3. A plus b equals 3. Always. We checked that on 200,000 random triples, and the identity never moved. The symmetry was not there, so we manufactured it out of nothing but a well-chosen companion. Now use it. Take the first term of a, x over x plus y, and make the denominator bigger by adding z to it. A bigger denominator means a smaller fraction, so x over x plus y is strictly greater than x over x plus y plus z. Do that to all 3 terms. Every denominator becomes the same total, x plus y plus z, and the 3 numerators are x, y, and z. So the sum of the 3 reduced fractions is exactly 1. Therefore, a is greater than 1. That argument used nothing about a in particular, so it applies to b as well. B is greater than 1 too. And now the companion pays for itself. Since a equals 3 minus b and b is greater than 1, a must be less than 2. One idea used twice, and both bounds fall out together. Strictly between 1 and 2. Now the other road, and here is where the argument turns on itself. Refuse to be clever. Put a over a common denominator and expand everything. The denominator becomes 2xyz plus x squared y plus xy squared plus y squared z plus yz squared plus z squared x plus zx squared. The numerator comes out as the same list of terms, except with 3xyz instead of 2. Every letter is positive, so compare the two lists term by term. The numerator is larger than the denominator, because 3xyz beats 2xyz. And the numerator is smaller than twice the denominator, because doubling gives 4xyz and doubles every other term as well. So the fraction sits strictly between 1 and 2. That is the entire proof. No companion, no idea, no insight. Just expansion and a look at the coefficients. This time the brutal road is the short one. The second question is harder, and it is where keeping the structure earns its keep again. Divide the top and bottom of each term by its first letter, so that it becomes 1 over 1 plus y over x, plus 1 over 1 plus z over y, plus 1 over 1 plus x over z. Name those three ratios x, y, and z. They are not independent. Multiply them together and everything cancels, so x times y times z equals 1. Now put over a common denominator in terms of x, y, and z, and subtract 3 halves. What comes out is a single fraction whose numerator is x minus 1, times y minus 1, times z minus 1. A product. So it equals 3 halves exactly when one of those factors dies, when x is 1, or y is 1, or z is 1. Translated back, when x equals y or y equals z or z equals x. The factorization was completely invisible in the original letters. Both bounds are now proved twice over. The numbers below are a check on the working, not a substitute for it. 300,000 positive triples, drawn at random over 4 orders of magnitude. For each one, we evaluate directly from the definition. The smallest value observed is 1.034. The largest is 1.970. Never at 1. Never at 2. Push the ratios to extremes and you can drive A as close to either end as you like. With the letters in the ratio 1 to 1,000th to 1,000,000th, A reaches 1.998, but it never arrives. The interval is open, exactly as both proofs said. And when we force 2 of the 3 numbers to be equal, A returns 1.5000000000 to every digit the machine will print. Now put the 3 problems side by side, because there is a point here that only appears at the end. In problem 1, keeping the symmetry was lighter. One idea, then routine work, while breaking it meant a discriminant and a hand-checked list of exclusions. In problem 2, the gap was even wider. Keeping the picture turned the whole question into a single observation about a point nobody asked about. And in problem 3, the elegant road needed an invented companion, while the brutal road simply expanded and stopped. So elegance did not win 3 times. It won twice and lost once, and it lost to the least imaginative method available. That is the actual lesson. Elegance is not a method you commit to. It is one of the options on the table, and part of the skill is knowing which day it is. Having several views beats having one good one. One more thing worth carrying away. Symmetric expressions are the ones that survive swapping. But there is a second family, and it is easy to miss. Take x minus y times y minus z times z minus x. Swap 2 letters and it does not come back unchanged. It comes back as its own negative. Measured, the value flips from 6 to minus 6. That is not symmetry breaking by accident. It is a structure of its own, called an alternating expression, and it turns up exactly where symmetric reasoning starts to strain. Once you know both families exist, the first question in front of any symmetric-looking problem becomes much sharper. Not how do I solve this, but which structure am I actually holding? So which road is better? Wrong question. Ask instead what each one costs. The careful road has exactly one hard step, realizing that a question about 3 numbers can be rewritten as a question about the roots of a curve. That single translation is the whole difficulty. Clear it and everything after is routine. The brutal road has no hard step at all. Nothing in it requires an idea. It costs you something else, a long stretch of careful bookkeeping where the only way to fail is to get tired. One road asks for an insight and then leaves you alone. The other asks for nothing and never leaves you alone. That is not a fact about this problem. That is most of mathematics. One last thought, and it has nothing to do with algebra. Handling something symmetric is like handling a good pizza. You can cut it carefully into 8 or 12 clean pieces before eating, planning first, respecting the shape. Or you can pick the whole thing up and bite into it. Both get you fed. One is a plan and one is an appetite, and it is fair to admit a preference for the neat cuts. That preference is not a rule, and the third problem is there to prove it is not. What all of this is really teaching is that the moment you notice a symmetry, you have been handed a decision, and that noticing the decision is worth more than always answering it the same way. 3 problems, 2 roads each, and 6 different kinds of work. Keep it or break it. Both are allowed.